So when we have a Cayley table for a group, this should mean that we don't have to do any new computations to figure out the powers of an element, right? Because all the multiplications of every element with every other element are here in the Cayley table. So for example, if I want to have this matrix, for example, and figure out what is its fourth power, then that just means I need to multiply it by itself 4 times, right? And I can do that with the Cayley table. So if I multiply it by itself once, if I get this matrix squared, I'm going to find it right here in the Cayley table. So if I sort of sketch that in, the second power I can find right there. Then to find the third power, I need to multiply this matrix by another one of these. But this matrix, because of the closure property, is also one of the entries here on the first column. Right? So I'll just take and then go down here, multiply that result by another copy of this, and so I find the third power right there. Does this make sense? And then because of the closure property, I can find this on the side again. It's right there. Multiply one more time by this same matrix, and I find my fourth power there. Right. So it turns out that this is 1001. So it's the great thing about having a Cayley table is it becomes, you don't have to do any new calculations. It can just be kind of a mindless property of chasing things around, chasing elements around the Cayley table. So what was the order of this element, by the way? 4, because the second power of this element was not the identity. The third power of this element was not the identity. But the fourth power is the smallest positive power that was. So if we're filling in this table, the order of that element would have been 4. How did you fill in the rest of these orders? So if we're reading across this row of matrices, what was the order of this one? That order was also 4. How about that one? 2. And then the identity matrix?
1.
Yeah. After all, the identity matrix is an identity element under the operation of matrix multiplication. Tell me about the complex numbers group. What was the order of 1 under the multiplication of complex numbers?
1.
That's the identity element in that group. Negative 1?
2.
And the orders of I
4.
and minus I?
4.
Also 4. Okay. So what do you notice about the orders of the elements in these two groups? Both groups have the same sort of set of orders, if you like, right? They have a single element of order 2, they have a single element of order 1, and they each have a pair of elements of order 4. Let me ask another question. Do you notice anything about the elements of order 4, let's say in the complex number group? In the complex number group, I and minus I both have order 4. What relationship in this group do I and minus I have to one another? They are each other's inverse. So somebody give me an I wonder if statement, which are the engine of mathematics.
I wonder if I is a generator.
Ooh, that's a good one. I wonder if I is a generator for this group. Let me put that one in the parking lot over here, because that's a great question. Is I a generator? It's not the one I'm interested in right now, but it's a good one.
I wonder if 0, 1, negative 1, 0 shares the same pattern.
Does 0, 1, minus 1, 0. Which pattern?
And 0, 1, minus 1, 0, and 0, minus 1, 1, 0 share the same relationship.
Same relationship as I to minus I.
Yeah, well, also inverse.
Sure, the same pattern as I and minus I. In fact, 0, 1, minus 1, 0 multiplied by 0, minus 1, 1, 0 is the identity. So sure enough, yeah, it's a good observation. Those two are the elements of order 4 in the other group, and those two corresponding elements also happen to be inverses to one another. So keep going. Now that we've seen this happen in 2 different circumstances, give me a conjecture. So we're observing here that we have 2 elements that are inverses, and those elements have the same order as one another. If I were to put an if-then around this, which order should we put the if-then, do you think? Could we put it both directions?
Yeah,
Okay. Let me leave that conjecture there for us to chew on. between now and Wednesday. Because there is a relationship between the very special monogamous relationship that is the relationship of an element to its inverse, right? It's monogamous because inverses are unique. I suppose there's one single lady in every group, the identity, which is its own inverse. And I suppose all the groups of involutions, every element of inverse, but inverses are unique, so that relationship between an element and its inverse, even if that element is itself, that has something to do with the relationship of orders. Question is which direction, or does it go both directions? So are these groups, the group of complex numbers, 1 minus 1, I minus I under addition, under multiplication, and this group of 4 2x2 matrices under matrix multiplication, we found out that the elements have the same orders. Now, what would it take to show that these two groups are the same? What explicit connections can we make between these two groups that show us that sameness? So what did your groups come up with here? One element of order 1, one element of order 2, two elements of order 4. And so to find an explicit relationship between these two groups is to correlate the elements with one another. So what's the element in the group on the left that corresponds to, let's say, the identity element in the group on the right? The element of order 1 in these two groups is what? 1 in the first group and the identity matrix, yeah, in the second group. So if I'm going to make an explicit comparison between these two groups, that comparison is going to be one that connects those two elements to one another, right? Maybe I'll sort of draw it like this. There's the first step in my comparison, that if I match those two elements up, they seem to be behaving in exactly the same way in both groups. Namely, they're both the identity elements in their respective groups. How about the element of order 2? Negative, yeah, well, well, actually, that's an interesting observation here, right? But it's an observation that makes use of more algebraic structure than we have on the table. But yeah, it looks like it's the opposite of the identity, additive inverse of the identity. The thing is, we don't have additive inverses here because we don't have addition in our universe. We only have multiplication. So we can't speak of it as being the additive inverse because there's no such thing as additive in these groups. But what that hints at is that we could put more structure on top of these. We could add a second operation, turn them into rings and not just groups. But we're not doing that yet. So we'll just suffice to say -1 and this negative identity matrix both behave the same way in the algebraic structure here. They both are elements of order 2. Now, what about the elements of order 4? Like if I were to take I, for example, in my first group, which element in the blue group, G2, should I correspond to?
-1, -1, 0.
0, -1, 1, 0?
Yeah.
0, -1, 1, 0. Why is that a fruitful comparison? Why does that make sense that those two would correspond? They have the same order. They're both elements of order 4. And what would that mean that -I corresponds to? The other one. Yeah, exactly. So -I would correspond to. That's the question I'm trying to get to.
Doesn't seem like it does.
Is there a reason for us to prefer one of these over another from an algebra perspective? So this is one option for how to correlate these two groups, one with another, right? Is to assign, we're forced to associate one with this and -1 with that because they're the only elements of orders 1 and 2, respectively. But for order 4, there may or may not be a reason to prefer to associate I with this order 4 element and -I with that one, whereas what's the other option? The other way around. Okay. And it would seem like, from an abstract algebra perspective, it doesn't matter. Okay?
Yeah, they shouldn't matter.
This gives a pretty convincing rationale that these two groups are in fact the same. Right? But they're the same in kind of two different ways. Right? We have two choices for how to compare, how to relate elements from one of these groups to another one of these groups. Where have you seen diagrams kind of like this before? What am I, when I'm drawing little arrows like this, what am I kind of buttering you up to think about? What are these arrows representing? A function. Yeah. So it turns out that, yeah, you're You're thinking ahead of me. Yes. It turns out that functions are going to be the ways that we compare one group to another, right? A function that uses one group as its domain, the other group as its codomain, right? So here the domain is my group G1. My codomain is the group G2. And this function, let me call it phi. For some reason, algebraists tend to use Greek letters for their functions a lot. So why don't I just get us started thinking that way? So let's say phi is a function from G1 to G2, or phi if you like. I'm not sure how actual Greek people pronounce it. But yeah, so this has the property that phi of 1 is the identity matrix. Phi of 2 is not 2, sorry, negative 1. Right, it relates negative 1 to this opposite identity matrix. And then it relates I, so this is going to be the white arrows. It's going to relate I to 0, minus 1, 1, 0. And it's going to relate minus I to 0, 1, minus 1, 0. Right? So that's an example of a function that takes elements from G1 and relates them to elements in G2. What properties does this function have? Jimmy's already clued us into one. It's one property that this function has. It's a one-to-one function. That turns out to be the one that Jimmy didn't say, but it's right. Why? How can we tell from this diagram that it's a one-to-one function? Yes, different elements from G1 get mapped into different elements from G2. At no point are we taking two elements from my first group and saying that they relate to the same thing in G2, right? So it's a one-to-one function. What else is it? It's onto, because
you hit all of the outputs.
We hit all the outputs from G2. So this is a one-to-one and onto function. What do we call those? We call it a bijection. So bijection, you'll remember, when you studied sets in Math 180, bijection is the way that we can say that two sets are the same, in a sense, right? If I have a set A and a set B, and I have a one-to-one and onto function between A and B, then those two sets are the same somehow, right? Even if their elements are different kinds of elements. If I can show that there's a bijection, it shows that those two sets are equivalent in some way.
Do you have to specify that they're related through the order of their elements?
That actually gets to the next thing I'm about to say. Because groups are more than their sets, right? Groups also have these other properties that come from their operation. So the question is, don't we also have a bijection from G1 to G3? Let's call it psi or something like that, G1 to G3. G3 being the group with that I'm covering up here, the symmetric difference of sets. The G3 that we said was the odd one out. Wouldn't that make G1 and G3 the same?
Wouldn't that be assuming that G3 has the same, its elements have the same order?
Yeah, see, that's the thing, is that the language of bijection and set functions is not strong enough to make the comparisons that we want to make, such as the orders of elements. So that's what we want to go to, is that functions are going to be our tool for comparison, but not just any function on set elements is going to work. We also need that function to respect the operation of the group.